Hi, I'm Tom and I talk about code. Welcome back to another live stream where today I'm going to be working on my compiler that I am building in Rust. Yesterday was the 15th and it was struct time. Today is the 16th and it is still struct time. We made it halfway through my list. We added user types to my programming language. That means that you can make a new type, say, make a type called foo. I can't undo for some reason. What's going on? Excellent. I'm going to have to work out what's going on there. So we have user types in our language. You can now make a type alias. And I added struct definitions. So you can make a type called foo that is some struct. This has some weird quirks. To it, but it's going to be good. The parser works, the language works, and we started on field access. So that's where you have a struct foo, and you say like foo.x, right? It looks like this. So we get a pointer to a struct, because a pointer to a struct, usually you would use malloc or something for this. We don't have malloc yet. We haven't gotten that far into my standard library, and there's no memory protection. So we just make up an address, and this is now a pointer to a struct. And then we try and set one of the fields of the struct, and it turns out we need to kind of handle this as a special case. What this means on the left-hand side of an equal sign versus the right-hand side of an equal sign are slightly different things. What this is really saying is, out as a pointer to a struct, we know the offset of the field ptr in this struct. So we kind of take this address, we want to add 2 to it, and that is where that's the address that we write this value to. Now, funnily enough, that is also this is the wrong value. I probably want this to be like 4, right? Because this pointer should point to something outside of the struct, not inside of the struct. Okay, subtle thing. The fact that, let's make it a more different value just to make it more obvious, right? So this is like saying we have a list. The list lives at hex 1000, and the thing that this array is, the actual data of this array lives at hex 2000, and it has no length. All right? So that's what we're trying to do. And we started implementing this left-hand side, right? We started implementing this. This is kind of like saying, this is actually exactly like saying out plus 2 equals 2000, right? Because we know the offset of this thing, plus 0. We know the offset of this field is 0. It's the first field in the struct. So it has an offset of 0. So we take whatever this pointer is, we add something to it, and we dereference it, right? But we need to do this in a slightly smarter way. We need to look up the name of this field in the struct, right? We need to resolve a bit of information at compile time. So let's look at our code gen. We started doing all this stuff. We started doing this big refactor, and this block of code is really ugly. This is really not good code, and this is not the way we want to be doing this in the long run, because we have to do this really awkward check where we say, we destruct the type to see if it's a struct, but then we also have to check to see if it's a pointer to a struct, but actually we're going to treat these the same, which is extremely jank. It's really not great. So the way all of this if-else logic works, the split on these block variables where every other type other than a local is currently unsupported, we're going to have to rethink all of this at some point, okay? We're going to have to rethink all of this, but for now we're just going to press forward with this really dumb solution. The other thing is I've hard-coded this. So, we have out.ptr, right? But, and also I'm gonna make this maybe a comment. We have out.ptr, but what if I have out.foo.ptr, right? What if I have out.foo.bar.ptr equals, what if I have out.foo.bar.baz.xyz equals, how we can go many layers deep. We can have nested structs. So right now I'm assuming we're only going 1 layer deep, but then I'm going to have to modify it to do multiple layers at once. And this is just going to be, offsets of offsets, I guess, right? That's fine. You can just add all the offsets together. That should be fine. I don't think that's actually hard, but anyway. Unless they're struct pointers. So let me go back to this real quick. So if we have a struct foo within our outer struct, or a struct field foo, which is a struct, then we add the offsets. But what if we have a field bar, which is a pointer to a struct? Then we add an offset to, we kind of reset our base, right? So we add offsets, and then when we hit a pointer, we have to get the value of that pointer, and then that's our new base, which is kind of confusing. And that has to happen at runtime. Okay, so there's a lot more here than I bargained for. There's a lot more here than I bargained for where we do this, where we step through this. There's a lot there's a lot more than I bargained for. But let's just keep doing the simple thing. This is my approach. We do the simple thing. We do the dumb thing. We fail. We find problems and we fail forward. Okay, so if I look like I'm standing weirdly, it's because I've got a heat pack wedged against my bum just to try and keep me warm because it's really cold today. It's really, really quite cold in here. It's like 10 degrees Celsius inside, which isn't nice. So we have a field type and a field offset because we have gotten the field. We have the name of the field. We have the expression we want to write into this slot in memory. That expression goes on the stack. Then we put the address of that local in register C. We work out the field type and the field offset. Now, the type is important because in this case, because this is the last thing, the type of this field, it must be assignable, or the type of this overall expression must be assignable to that RHS type. So RHS type dot assign can assign from. So this is field type. So if we can't assign from, if we can't assign from the field, the right-hand side type, so if we can't assign whatever the type of the expression on the right-hand side is to this thing, maybe because it's too big or because it's unsupported for some reason, for example, we can't assign a struct to another struct. I don't do that kind of value copying. You'd have to use a memcopy, except, I haven't written memcopy yet. If we can assign from the right-hand side, if we can't assign from the right-hand side type, then we need to send back a type error. And I'm just going to copy and paste one of these from before, type assign. Oops, didn't mean to do that. I love when you have accidental Vim madness. Okay, so from right-hand side type to the field type. This is going to generalize really, really badly to more than one thing. Whoa, oops, moved my thing. Emo Giraffe with an interesting comment here. We're going to pull this over onto the screen. NVIDIA is making you regret the day you decided to try Linux. Probably soon the day you were born if you don't manage to get the proprietary driver to run for your deprecated Stone Age laptop GPU. That is rough. I'm really sorry to hear you have such an old GPU. I'm a huge Linux fanboy, but I do also admit that older, sometimes unsupported hardware, or sometimes less supported hardware can be a bit of a nightmare. Is Nouveau not an option? But how old are we talking here? Like, how old is this NVIDIA GPU? Like, how old is this laptop? Wait, how long have NVIDIA been putting GPUs in laptops for? But no, I am sorry. That is very dramatic and hard to deal with. And, unless you want to become a GPU driver expert, it can leave you a bit up shit's creek. Okay, so we can assign to this thing. We have a field, we have a value, we are allowed to assign to it. So the address is, we don't use colon equals here. That's in my language, not in Rust. It's really silly. Okay, so the address is whatever is in register C plus this offset. So we want to say out.push unresolved instruction, except it's just an instruction. And that is going to be an instruction. An unresolved instruction, it's the add immediate instruction, right? Because we want to add something to whatever address is in register C. So we're going to have register C, and we are going to add literal 7-bit field offset. Except this can error, and we're going to unwrap it. Because, we shouldn't have so many fields that we overflow a 7-bit in, right? You want to daily drive Linux Mint for everything, including gaming. The gaming experience is poor. GT 720M isn't much worse than Windows. Like, that's a pretty old GPU just in general. I don't imagine you're having a great experience in a lot of places. Sigo Null, welcome back. We're picking up where we left off yesterday. We are gonna do a struct. We're gonna do it. Because we get the address in register C, then we're gonna pop the value into register B, and then we'll write register B into the address in register C. Perfect. We're going to do the old copy and paste because typing all this stuff out for unresolved instruction is really hard. Unresolved, we're going to do a stack operation. We're going to go register B. We're going to pop from the stack pointer. Excellent. And then we just need to do the store byte, store word. This is also hard. It depends on the size of the thing. So, and this is also why we don't do structs by value, because this gets a lot harder. I think I literally just check, right? Store word. Okay, apparently I don't use store byte anywhere, and that's kind of a problem. Like, we kind of need to check this, right? We'll say out.push, and we'll say write. I will say out.extend. Write bytes. We'll say write value. We'll say, I think this is okay. It's the type of the field. No, it isn't. It's the right-hand side type. And it's register B. I'm going to try and abstract all these things out to functions where I can. Okay, so we take this thing, we take the type of, we'll call it ty, the type of the thing we're writing, which is a type. We'll take the register with the address, the register with the value, which is going to be a register, and the register with the address, which is also a register. And it doesn't return anything. Okay, so we say if match ty.size bytes. If it's 1 byte, then we want to say out.push. We want to use the store byte instruction rather than the store word instruction. This is probably the cause of the memory corruption I was seeing when I was writing to the virtual screen the other day. That would make sense, right? Because I'm writing 2 bytes at a time, and that doesn't really work. Instance review system, black screen, desktop environment. Desktop environment is gone. Like, even when you swap back to Nouveau, you don't get a desktop environment, because that would imply you've really messed something up. But if you can swap back to Nouveau, that just sounds like, yeah, the driver doesn't work. Once you're installing from their website, you're going to have a bad time. Have you checked the Arch Linux wiki for your specific model of laptop? Because that's the place to look. Okay, so we need to, we're storing the byte, we're storing reg. I need to double check. I want to make sure I get the order of operations correct. Base page address. Our base page value is R2. Okay, so the base is reg adder. The page is register 0 because we're not doing paging yet. And the value is reg value. And we'll let cargo format work all the nitty-gritty details out, but that's good. We want to push this one instruction to our program. This is going to be the same thing, except we're going to push store word instead, store word, and then we're going to say anything else. Well, I guess 0 we might just return and just like do nothing. I guess we can also just say unit. If it's anything else, then we want to panic because, uh-oh, we can't assign this many bytes by value. Cool. Madflash19, compiler for which lang? This is my own language. I'm making it up. I literally am making this up as I go along. It's very C-like. It's very C-like. apt. Yeah, install from the distro repos where possible. Again, check the Arch Linux wiki. That will have your best case. Am I using LLVM? No, because I'm generating code for my own 16-bit virtual machine. That's why these instructions look a bit funky. Cool. So write value is going to be a good utility. I got rid of my mark. We also need to actually pass a mutable reference to the out vector. Okay, so we now have a utility for writing a value to a register. Like we set the values up, and then the instructions that actually do this, we have a helper function, which is good. Less copy and paste. Less copy and paste is good. Okay, so if this is a struct, but what if it's a pointer? If it's a pointer, we want to do literally exactly the same thing. And I'm just going to copy and paste it. Even though this is bad, I'm just going to copy and paste it. Because I just want to see if it works. And there's naturally some problems here, right? Naturally some problems. EXPR is not found in the scope. That's because it's called RHS. Cool. SF. Can't find SF in the scope. Yep, that's good. Because if it's SF. If it's a pointer T, sorry, we need to say if let type struct SF equals T. Or we need to say pointer type struct SF, right? We can nest these unwrapping. You spent 3 days with Linux, been a Windows user your whole life. Look, yeah, it's hard. It's hard when you use weird unsupported hardware. It really is, but try and stick with it. I bounced off of Linux a few times before it really stuck. You know, even if you go back to Windows, you can play with like VMs. It's worth doing, but it's good. Did I use a parser combinator? I wrote my own parser combinator library, yes. I did it all from scratch. I have basically no dependencies in this whole project, which kind of feels good. So obviously if I'm compiling to WASM, I have dependencies. Otherwise, there's no dependencies in the VM, and the language depends on RAND, and obviously the actual virtual machine crate. So that's fun, right? It's been good doing this all from scratch because the goal has been to learn about Rust. Okay, type of needs a block scope. So I guess we just pass the scope in. Except we need to borrow the scope to pass it in. Cool. Expected expression. Oh, we need to borrow the expression as well. Nice. Right hand side type can assign from mismatch types. What is this? Oh, I expected a ref to a type. That's good. Expected type. Now this is the opposite thing. So we need to clone here because we don't want to deal with a ref. We can't spell register. Thankfully, I didn't copy and paste that everywhere. Field offset. Expected U8 found ref usize. Oof. As UH. We need to cast this bad boy down. Expected box type. Can I unwrap it? Can I unbox inside here? Can I match against a box? Rust match box T. Is that legal? Am I gonna get kicked out of Rust Club for doing that? Yeah, how to pattern match a box. But this is a nested, hold on, Rust match nested box T. This is what I want. Is this code on GitHub? Yeah, hold on. I don't have Nightbot set up, so we have Tombot instead. No, don't apologize for your Linux rant. I welcome a Linux rant here, and you know you're gonna find good people who want to help. You're gonna find, you know, the people around here. They're gonna push you to stick with Linux and try and help you out. So you're welcome to come and talk about Linux troubles in this chat. Always, 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 always. Common questions. Currently stable Rust, single level. Yeah, matching against boxes aside isn't redundant information. Okay, no, that's not nuts. They're just showing me a different way of doing it, which isn't right. I wonder if this is probably still true. Okay. Okay, we need another layer. We have to go deeper. T. If let some, because T is a box. If type struct sf equals star T, right? Like dereference it as a box. Then we have to do all of this. Up, down to the right value. Otherwise, oh gosh, this just feels really gross. It's this thing again. Can assign from, oh yeah, a couple of things that I didn't fix up over there. This, I did copy and paste the typo. I knew I'd copied that somewhere. Field offset, I also need to say as u8 because we're casting it down to a 7-bit int. Okay, there we go. So what happens if I build this right now? It's gonna yell at me about a few things, right? One thing is that I don't actually have comments yet, and also there's a bunch of random garbage here. So that's cool. So this should actually be able to compile, and it does. Oh boy, it does. Okay, so do I test this out? Do I just dump this into Xclip and see what happens? Rust simple VM. Sorry, I just need to run my web server so I can actually connect. So if I build this, it looks like it builds okay, which is cool. And we jump into this make array. So we would what do we expect to actually happen here? What am I looking to happen? I want to see the memory address 1000 get written. Now, I'm gonna, oh, I might have it enabled already, actually. If we can just like tell, there it is, DWM to snap everything together. Not to out that this window in my stream is fake, you know, and there's an entire window manager running in an entire desktop just in this little fake window here. Like it's just a fake title bar, guys. It doesn't exist. I can turn it on and off. It's just part of OBS. So if I look at the console, we can see all of the reads and writes that happen. And as I step through this, I want hex 1000 to get written. Okay, as we come through here. So this is where we set up hex 1000 in register C, 512. Wait, what's that? Is that hex 1000? I need to double check. 0x 496. Okay, that's two. Hold on, that's 2000. Yeah. Sorry, that's right, because 2 to the 10, 2 to the 11, 2 to the 11, 2 to the 12. Yeah, like something like that. Yeah, because 1, 2, 3. I don't know. I feel like this is right. So we're gonna try and write this value. We're gonna try and write this value to hex 1000. So we're setting it up. We expect to get the address here. That is right. And we're gonna store the word in C right at like that. That doesn't look right. I think something went wrong. Okay, hold on. We do 2 B pops in a row, which is certainly not correct. Is it possible? Is it possible? Ah, yes, it is possible. I obviously forgot to change something here. But what was I doing? We add the immediate, we pop the thing. I think I just duplicated this instruction. I think I copied it because I was gonna do something, and then I just didn't do that. So that's cool. That's cool. The biggest bug, as always, is just not understanding your own code. Let's jump in and recompile that, and we'll see what happens. We'll see what happens. We're gonna build it. We're gonna step through again, and we're gonna see all the reads and writes that come out, which is wonderful. Which is wonderful. So this is hex 1000, and this is hex 2000. So we should see NMC0. We pop this into B. And we write it into this address, which is not right, which is not correct. Oh wait, hold on. Maybe that is correct. Like it isn't, but maybe it is. Because we get, oh God. Yeah. Sorry, that's not right. My code gen isn't right? So where are we writing this to? This random thing here. What's this? This is the address of the first local that we can see because it's the value of the base pointer. So this is the first local in this function, right? So if this was an array that we were allocating, you know, like 0 initializing or something, this syntax doesn't exist in my language yet, but if we were doing this in theory, then yeah, this is the address we would want to be writing to, but we're not. We have a pointer to a struct, so we need to do one extra level of indirection. We have the address of the struct in register C here. So before we add anything, we first need to dereference that. So we need to out.push unresolved instruction, blah, 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 blah. Wait, where is, so C, local address 2. And we probably want this to happen after we've done our type checking, right? We don't want to do any work before we've done our type checking. Cool. So we have an address in C, right? This local variable is a pointer. So the thing that's stored in the address, in the local variable is an address. So basically we need to dereference the local variable into an address, right? We have a memory address that we have, maybe I need to draw this. This is getting a bit hectic. There's a lot going on here. I'm really sorry. There's no way to get around this. There's just a lot going on. So we have our stack, right? We have local 1, we have local O, we have the old base pointer, we have the old program counter, and then we have arg0 ... arg n, right? This is a stack frame. And in local 0 here, we have the type of the variable that's being stored here is pointer to array, right? And the value of this type is, the value in this variable, sorry, is hex 1000. So we need to get the address of local 0. So let's say address of L0 equals, 63,580 or whatever this big number was, right? This is the address that points to this spot on the stack, right here, this thing here. So at that address, we read that address, we get this value. Read this. Then to get any of the data actually associated with the underlying struct, we have to then dereference again a second time. So there's like another dereference here. Okay? I hope that made sense. I hope that made sense. Because holy shit. It's going to be worth it, all right? So I think all we need to do here, we've got an address. All we need to do is load. So this is a pointer. We know it's a pointer. So we want to load word. And I'm going to double check the order of things in load word as well, just because it's good to not make mistakes. Base page. Okay, so we load into register C. We load into register C the word at the memory address of register C. In other words, whatever is in local 0, whatever we've stored in local 0. There's an extra level of indirection here that isn't in this one. That should be okay. Also, I'm going to move this here too. We only do code gen after we've done our error checking. That's a good principle to adhere to in general. Okay, so that builds. Let's see if we can get this to run. Build. Okay, we're going to do our usual favorite thing of step through a bunch of code. Step. Okay, so 4096, this is good. We pop. Okay, so we've got this on the stack, and we've stored it in our local as well. We set up the address that we want to write, and we want to write this to address hex 1000, which is 4096, I guess. So we push that to the stack. Okay. We get, yes, this is right, this is right. Now we add 0 because that's the offset. We pop the thing we're writing. So this is it, we're doing it. Now we write to hex 1000 and hex 1001. We write this entire word to this word address. So this is correct. This assigns as expected to a field of a struct. The code is freaking disgusting, but it works. It's a good start. Okay, so how do we make this not suck? How do we make this not suck? First things first, there are a few common things here, right? There are a few common things. So it doesn't matter what we do. Doesn't matter what we do here. Index. It's hard because we need this type. We need this type. So maybe we can say let bv. So we'll get the block variable, and we'll get the type up front if we can. So this bit here. And actually it is with a question mark. Okay, so we have the block variable. Now we're going to say match bv. And we're going to do a much simpler preliminary match before we do the actual code gen. So index, we don't care about type. We just give back the type. If it's an arg, we give back the type. I think there's a pattern here. Hopefully you see it. If it's a global, we give back the type. And if it's a const, we give back type int. So this is the var, the type of the variable, the type of the thing that, the thing on the left-hand side. This is like the stub, right? So we need this thing to be a struct because we're getting a field of a struct. Okay, so my keyboard keeps just kind of losing connection, which is annoying. So. BV. This is hard to unpick. This is really hard to unpick. So we have the type, and this is good. We can do this up front. We don't need, this simplifies things quite a bit. There's still going to be some specific code depending on the thing, but we can make this a little bit simpler. So we have the type. Now we need to work out if this type is a struct. So we're going to say let struct, let type struct, let struct fields maybe equal. So we're going to match on this type. If the type is a type struct, then we're just going to give back the fields. That's good. If it's a pointer, then we do this thing. We're just going to copy and paste this logic. So if it's a pointer, it has to be a pointer to a struct. If it isn't a pointer to a struct, we get an error. Struct sf, we give back sf. Otherwise, error. Otherwise, return. And it's this error that we have already written down here. Cool. We just copy and paste. Copy and paste. Excellent. Okay, so hopefully you can see why this is beneficial, right? We're doing this complicated extraction up front, this complicated nested type stuff. Now all we need to do in here, we need to check if we can assign the field. We need to get the field. sf.get. Okay, so now we can just do this up here, right? We can say struct fields.get. And we have a field, right? So this is one less thing that we need to copy and paste. And let's again actually just do this. Field type. Now again, we can do this assignment from check up front. What is going on? Damn, I've been pretty good at eyeballing my indentation multiple at a time lately, but not today apparently. Okay, so this is good, right? So all we're saying is, oh, hold on, pointer. We also need to know that it is a pointer. And we're going to do this gross thing. We're going to do this really gross thing. Actually, there's another way we can get around making a mutable variable, right? And that is to say, okay, I think we got this. So everything under here, right, is ugly. Ooh. There's a few things that need to happen for this code to work and to be a bit more generalized. There's the bit where we have to load address of thing based on variable type, where thing is either a struct or a pointer to a struct. And we optionally do an extra dereference based on if ty is a pointer. Then once we have it, and this goes into register C. Then everything after this is fine. This is all the same. Add field offset. Pop value to write from stack. Okay, so this is the only bit that depends on the actual type of the thing. So again, we're going to have a second match statement here, except with this extra bit too. So from the if pointer parallel universe, where we have to do the extra load word, and I'm cutting and pasting because all this stuff's going to get deleted. So we add the field offset before we add the field offset, right? Before we do that, we've got to We've got to do an extra thing. So before we add the field offset, if the type is a pointer, then we have to resolve C from an address into a thing. We have to do this step, this thing that I drew, this weird thing that I drew. Only if this is a pointer. I'm pretty sure we have an is pointer. Beautiful. Okay, good. This is going to be a lot easier to manage now. Now we have to do a second match, right? We do one up here just to extract the type. Now we're going to have to do one that works on the index. So we're going to say match BV. But this just has side effects. This doesn't actually resolve into a value. So load the address of the thing. Now how do we do this here? So if BV is a block variable local, we get the index and we ignore the type. All we say is, and actually I don't even think we need the braces, all we say is, what's it called? Load local adder 2. This is it. This is all we need, right? We load the address of the local at this index into register C. Beautiful. And we can do the same thing for an arg. Block variable arg. Load arg address into register C. And then anything else, we're going to just put a to do const, and actually we can print it out, right? BV in struct field. Right, all we need to say is, hey, we're assigning some fields in a struct and we've encountered a variable that I don't know how to deal with. And now I can get rid of all this weird stuff down here. This was good to learn, but it was a bit redundant, a bit repetitive. So look how clean this is now, right? It's good, right? You do a first pass that sucks, and you do a second pass that I guess still kind of sucks, but at least it's more human readable now. So I'm gonna run this and it's gonna almost work. Almost work. Does this need a semicolon as well? I don't think it does. 255. Yep, that does need a semicolon. This also needs a semicolon. Couple of semicolons short. Match ty. Oops. Extra character. Match ty not found in this scope. Why isn't that found in this scope? Because it's not called ty. It's called var type. Struct fields. Just have to use the right types. That's good. BV is correct. Var type. Potentially moved value. Oh dear. Is that because when we match, we have to match a ref instead of a thing? That might be why. We might have to match a ref. Match. I guess because because we're using data from within the thing. Prof Element says structures containing structs and seems very distressed by this. I am also very distressed by this. Welcome to the meat grinder. This is rough. But we're gonna get there and we're gonna do good stuff. I think because this match expression returns something from this outer structure. If we don't ref it, it gets moved. I think that's what happens here. Match arms have incompatible types because this now needs to be. Is it okay if it's a ref? I don't know. We'll find out pretty quick. It should be. Box resolve type. Okay, expected box type found type. Do I need another star? Is that what's happening here? Weird. Match arms. This is not a hash map. Expected a hash map string type usize. Found hash map string type usize. Oh yeah, okay. Can I return a ref? Is that okay? Is that allowed? I think that's fine. I think that works. I think we can do it. You're casting usize as u8. Yep, that's good. We can do with that. We just need to put a star there. Love it. Okay, we're getting close. We're getting close. Cannot move out of T. Struct behind shared reference. Data moves here. SF has type hashmap, which does not implement copy. So we can't dereference. We can't move out of this. And that makes sense. This is why this kind of pattern can be really hard to deal with, right? Especially when you have successive things on the same data, because, you know, nesting it inside here, like putting everything inside these curly braces makes the ownership really, really easy to reason about. Putting on the outside, oh boy, that makes the ownership really, really hard to reason about. Makes it really hard, really easy to do things wrong. So, you know, if you've seen this kind of pattern in Rust, right? It's easy to do the wrong thing. Now, here's something we can do. Var type. Yeah, so what I'm going to do, I'm going to hand out clones of this type. So instead of being a reference, it's just a value. We don't get a ref to a type, we just get a type. And actually, this doesn't need to be cloned. This is a bare a bare enum value. We don't have to clone that. That's a bit redundant. Okay, make B. Now, can I do this? Yeah. Okay. That's better, I think. Value partially moved here. 251. That's here. The 3 reinitializations might get skipped. 25 partially moved. Borrowed here after what the hell is a partial move? I've been writing Rust for a couple of months now and I've never heard this word before. This is kind of hard. So this isn't going to work, right? The suggestion that the compiler is making here is saying turn this into a ref. Or wait, which one is it saying? Which one is it saying should be a ref? 257. It's saying this one should be a ref, which is weird. Taking members out of structures is a partial move. That makes sense. Okay, so we're not moving the whole thing, but we're moving something from inside of it, right? That makes sense. Hold on, there's another thing I can do here, right, which is silly, but I can also just put a clone here. Won't that work? Yeah. So I'm learning to understand Rust, right? This is silly. This is really, really silly. And actually, hold on, I'm going to go back. I'm going to wind this back and make these refs again so that I minimize clones. I think this works, yeah. So as long as I clone here, and I only need to clone once now. I don't have to do this weird clone and then clone again thing. I give back a ref to a type, but here, because we need to move some of the data out from the type, we have to clone it before we do this match, or like as part of this match. Okay, so that kind of works. That kind of makes sense. I'm understanding it. I get it. Thank you, Prof Elements. That did actually help as well. Like when you see partial move, you're like, what the hell does that mean? Then you see someone saying members out of a struct is a partial move. You're like, oh, partial is in part of a struct. Like that makes a lot of sense. All right. So we get this cool thing. We're going to see the address come into... So the address is in C, the value is in B. We're going to do this add... Oh no, we do the store. We do the store right now. And we write it. And we see the write come in, which is good. And so it looks like this still works. It looks like this is still behaving itself. But it looks like we could also do fun things now, like test.code. We could say void set ptr. We could take an array and we could let's say set len. That maybe makes more sense. Int len. We could say a.len equals len. Right? I think this is good. So we could pass an array into this function. We could say set len y. That doesn't quite work. That's a compiler error. Is it? I don't even know what this is. Let's get rid of this X clip, and let's pipe everything 2 goes to and 1. Okay, so what is this? What's happening? This is the context. No struct field reference A. Okay. Oh, it's saying that A is not a struct. I think. No, non-struct field reference. Non-struct field reference A. So non-struct field reference we give out if the thing we're pointing to is not a struct. Which doesn't really seem to make sense here. Really does not seem to make sense here. Head, of course, is this thing A. So we check the type. The type is not a struct, right? We know the type's not a struct. Let's just do this again. Do I get local count, args. Oh yeah, args, sorry, that's the one. Args, make array args A, which is a pointer to a struct. So this looks like it's correct. Setlen, we have a function called setlen. It's a function definition. It has args. We can see it has an arg A, and the type of that is a pointer to a struct, and that struct has fields ptr, which is at offset 0 and has type void, and len, which has offset 2 and has type int. Now, just to rule this out, in case I'm doing something really silly, let's just see what happens. Okay, so that's good to know, right? That's good to know. It's good to know that this is not related to the field we're trying to dereference. R point is 16 bytes in my compiler, yes. Yes. My machine supports addressing 32 bits. 16 bytes, sorry, 16 bits. I've still been doing PS2 dev slowly in the background, so 16 bytes is also a key number there for 128-bit big words. But yes, 16 bits. So it's a little bit limited in what it can address right now, but you can reference a full 32 bits. There is a page register, or you can use any register as a page register when you do memory reads and writes. But I currently don't generate code for it. I might add a long pointer type in the future. And that'll be fun. They'll have really bad performance, but you'll have the option to address more memory. That's my thought. That's my kind of vibe right now. Okay. It'll also be weird because, like, I'm going to do some register allocation stuff at some point, and they're going to be so register hungry because you really only have 3, maybe 4 general purpose registers. So having 2 of them get taken up by an address is pretty significant. But it's fun, right? It's all part of the joy of writing for a weird esoteric virtual machine. You have to work around these requirements that are completely arbitrary and invented by me. So we can work with structs that live in locals. But for some reason, we can't seem to deal with this struct that's defined as an arg. So why is this not... Wait, what do we actually get here? I guess this is the other thing, non-struct field. So we have the thing. Let's also include the type of the thing. That makes sense. var type.clone. I'm going to put this in here. Var type.clone. So we need to go into errors, and when we have non-struct field reference, we're also going to have a type. Here we go. So non-struct field reference A. It says A is an int. It says A is an int. Have I made a horrific typo? This is question number 1, okay? Because is this somehow being misinterpreted as a const? Is that possible? Surely not. Surely not. It is a pointer. No, it isn't. So it's not... Okay. I'm going to panic here, just so I can dump some more info to the screen, which is silly, which is really, really silly. Head var type. And we're also going to do BV, right? And we're going to see what this thing is that has caused this panic. Panic. BV doesn't have a display. We're gonna do this. Any code following this expression is unreachable. A is an int, and the arg is defined as an int. I have a suspicion about why this is the case. I have a real sneaky suspicion. Let's find define arg. Do you see what the problem is? Define arg. Args.push. What are args? Args are just strings. So when we get arg, we always say the args are int. Args always have type int. So we need to fix that. We really need to fix that. Let's start at the top. Let's give back a type. Let's give back a type. Return some I. Args iter enumerate. Function block dot args. Function block. Fn block self parent func dot borrow block block. Parent func is a block. Struct block args. We need to do this thing. Go vec string type. Okay. When we define an arg, we also need to take a t type, and we're gonna push a thing and a t.clone, because again, we want this to own it. Okay, and then when we get a thing, it kind of is already supported, but we're gonna get a type as well here, and be able to hand it back out with the arg, which is good. Get arg is gonna for I k t. Cool, so we're just gonna get the types as well, like we're doing here. This is yep, that all looks good. We might need to clone. I guess cloning is good. Oh, just got an interesting message. Nice. I think this makes sense. Okay, define local, and then define arg happens down here. Now when we build this, a couple of things are going to break and yell at me. And we're just going to have to step through everywhere we define an arg. And now, where we were ignoring the type before, arg type, we just pass it on through. As a ref, I don't know if we need to do it as a ref. Resolve.type found ast.type. So we need to say type.from ast. I forgot. We need to do this conversion, and this is good. It feels like we're moving these conversions up front more and more. We're putting these conversions at the forefront, so that we're not passing these weird AST objects around while we're doing code gen. Okay, where else do we call this? We call this here. Cool. We need to not call this type. I think you can also, what is it? Is it like hash r or something you can say? But I would rather not do that. So we need to say type.from ast arg type. This might complain that they're not refs. It does. Oh, and I need the context, don't I? That's funny. And then let's do that. From AST, we need to go context, and then we're gonna, oops, make this a ref maybe, just to see what happens. Expected type found result type. Yes, this resolve, it gives a compiler error, so we can just put the question mark in there. Expected type found type. This needs to be a ref. This also needs to be a ref. Okay, what else have we got? Expected context found context. This needs to be a ref. Gosh, unexpected ref The trait from compiler error. Ah, yes. This is also this funny thing where I need to map. I need to enrich this with a context. I need to enrich this error with a context. We give back the context along with this error. Wonderful. Okay, so this works again, which is really cool. Let's copy this to the clipboard and run it again. See what happens, see what it looks like. Right? So when we call setlen, we should see the correct offsets go through. We're going to look for PC162. I really need to be able to set a breakpoint. That would be a lot easier. But that's okay. That's okay. So we're going to do some stuff. This all gets set up correctly. We write something. That's not quite the address I expected. Pointer. Oh no, that is the address we expected because we write 0 here. We write, where is this? Where's the first write? I can't see the first write, but the second write is correct. We set 0, which is cool, Oh, I don't know why this compiled. I'm not actually passing the correct number of arguments. Do I not check the number of arguments? It's kind of funny. There's a to-do. There's one for later. So let's build this. So we should see im82, and then we push, and then we do some stuff, and then we should jump somewhere eventually. PC, yeah, here. So this is where we function call down to line 166. Okay, so we want to see PC166. We're going to go through, we see these things go through the registers where C and B have the address and value. We do this store word, we see the correct thing is written, then we're going to see this offset get written. Because 2 gets written to C, we're going to pop the value, we're going to write it, we set the length to 0, which is cool. We can continue to step, we go back, then we're going to push some stuff to the stack. I don't have a breakpoint system for my VM. It's hard. It's really hard when you build all the tooling yourself, right? You're like, I'll get to breakpoints eventually. But the UI for it is non-trivial. Right, this is all. I'm just like messing around. There must be an editor I can pull in, right? Someone's like text editor that would make this easier. Maybe not. Okay, so here we go. We're in setlen. I really need to optimize out some of these instructions that add 0 to things because they're no-ops. They don't do anything. Adding 0. No op. Okay, so we're going to load the number 82, which is good, and we're going to push it to the stack. Then we're going to load the address, and then we're going to add 2 to it because we're setting the length. And then so we've got the address in C and the value in B, and we're going to store the word, and we can see the length as we expect it is written, which is good. So it looks like structs work. This is a working struct. The lack of malloc is a little bit of a problem, but we have a working struct. The only thing we're missing is the ability to initialize them on the stack. Or like as a local, I guess, right? Like we should, in theory, be able to have have stack frame local variables that are structs. We should just be able to handle that. Now, I'm going to look at one thing to see if this is feasible to do today. Local. Well, actually, let's look at 2 things. I'm going to look at how locals are defined in a block scope, and they're a list of. They do have a size. Okay, they do have a size. That's good. I also need to look at the code gen when we have a function definition. What is it? Compile body. This is when we compile a function. Okay, so one of the first things we should do, label, we should have, an add immediate where we add local count sim. And we define this as the local count multiplied by 2, which is decidedly incorrect. This is not how we do locals. There's a chance that if I naively change this, having cars will break things, because cars currently occupy 2 bytes when they're defined as a local, which is inefficient, but because most of my code isn't smart enough to do this check, it's a bit of a problem. So here's what I'm going to do. We've written a lot of code here, but we've finally reached a point where this does actually work again. So we're going to add all of this stuff we've done in Lang. We're going to add all of this stuff from Lang, and we're going to commit it. This is everything. This is struct, parsing, and assign. Now this, cargo FMT first. That's good, that's good. I'm glad I added that check. Okay, so this is good, this is good. Oh yeah, this is nice. This is looking a bit nicer. Right value. We want to really make use of right value in more places. Everywhere we currently store a word, we basically want to be using right value instead. So what does right value do? Right value literally just takes the type, the value, and the address. Okay, so everywhere we have a store word, there are 6. There are 5 instances of store word outside of this function. We need to replace them all. Okay, and this is good, right? This is good. So this means that we can have cars actually occupy 1 byte in memory instead of 2. We can have densely packed cars. This is good news. This is a good thing. So declare, we have a type. We do have a type. And this is declare with expression. So instead of this, we're going to say right value. We're going to take a mutable ref to our variable. We are going to take the type, the value, the address. So we're going to take t. We're going to, actually, we need the type as it's been converted, which is var type. Wow, that's a weird statement. Right value, it's going to be var type. Var type, we're going to have register B, and we're going to have register C. And I think those are backwards. Value address, yeah. Value, in this case, is in C, and address is in B, because it's backwards compared to how I've done it other places. So this means that if we only have a car, we're only going to write a byte, which is good. Densely packed cars. Do people say chars? I don't know. I always feel weird if I say chars. I feel like people are going to think I'm like a weird nerd. It's a car, right? That's how I'm doubting myself now. And I've got a rare moment of self-doubt. Oh yeah, the other thing I forgot to do before I committed just then was a cargo T. I really hope all these tests pass. Yeah. Whew. That's a bullet dodged. A bit scary there. Okay, so we're gonna march forward with our right value, and this is the same thing. This is literally the same thing, which is good. And here we're actually using this other fun function called load address to, where we get the address of a thing and we put it in the B and M registers if it's a bigger address, I guess. Which is a fun utility, right? This makes all of our code gen simpler and more flexible. And then we also use right value in the same way. C has the value, B has the address. And we're ignoring long pointers. At some point, we're going to have to consider these extra registers that, you know, may have other stuff. But for now, we are dealing with short pointers only. It's a nice little optimization. Here, C has the address and B has the value. So it's like this. Because consistency is hard, right? Consistency is really hard. And here, B has the address and C has the value. And I'm going to write it out again because I lost my buffer. This has... Oh, all those types are going to be wrong, actually. All these types are called weird other things. Now, we need to know the size of this local. We need to know the type of this local. Assign from stack to local. It's only used in one place. Okay, so we're just going to pass the type through as well. We're going to say type, ty, maybe as a ref. Then all we need to do is keep passing this through. We have the type. We get the, now, CB. We have register C is the value and register B is the address. And I think I still did that backwards. Value address. C is the value, B is the address. Yeah, okay, that is right. That is actually correct. Cool. So taking a value on the stack and assigning it to a local. This is good, this is good. If I build this, we're gonna get some weird errors because I copied and pasted and I didn't really think about what these things were called. Expression type of TT. I guess that's a type, not an AST type, which is cool. Where are our other right values? This one is var type. This one RHS type. That's good. Right value ty. That's good. Right value. Var type not found in the scope. This one. Oh right. Yeah. Compile expression. So this one, we want the type of the right hand side. Let's say let type of. We should really check that we can assign between these two things. We should we should really make sure. What even is the type of the left hand side here, right? The type of the left hand side is, well, I guess whatever the thing is, right? So if it's a car, if it's a pointer to a car. Well, no, if it is a car, how does that work? Anyway, we need to think about that. We're not going to think about it right now. To do check, we can assign. Because, you know, if you try and write, in this case, we're going to do the type of the expression, I guess, but in general, you want to make, no, we should do the left-hand side type, But in this case, we're going to say the left-hand side is a car pointer for this assignment deref. An assignment deref is like saying star x equals 5, right? If x is a car pointer in this case, then we're going to try and write a byte. But what if we try and write an int, right? Then we're gonna put the wrong thing there. We kind of maybe need to check that ahead of time. But also maybe not. Maybe we just do the C thing and go by the left-hand side, because I think that's all C does. If you tell C it's a car pointer, it'll write a byte. If you tell C it's an int pointer, it'll write 4 bytes, or however many bytes an int is. In my case, an int is 2 bytes. So we're gonna have type of, we're gonna have the context. I think I need to give a ref to the scope as well, and we're gonna take the left-hand side. Left-hand side type, cool. Yep, that's how C does it. It really is, isn't it? Like, maybe my language should check this. Maybe I should be a little more strict than C. Just a little. Oh no, right value expects a type, not a ref type. But this really should be a ref. We really do want a ref here. It just doesn't make sense to copy. Okay, what's this? Type of. This is very good as well. I like this. This makes me happy. Type of. What else is wrong with type of? Type of just doesn't fail. It just gives us back a type. I feel like it should fail for some reason, but it doesn't. Left-hand side makes the most sense. You're not going to go wrong, right? You're not going to... Like, the left-hand side, in theory, knows what type it is. It's like, you're not going to... Like, if you go by the right-hand side, it's like you have a car pointer and you have an int, and you write 4 bytes. And it's like, well, what does that even mean? What does that even mean? All right, what else have we got? This is going to be extremely subtle and annoying. Oh dear. Value borrowed after move. Values moved. Moved here. Oh, so I can do this first, maybe? No, I still get this. Do I still get this problem? Can't borrow is mutable. is not declared as mutable. What? That's because it's already a mutable ref. You can't double mutable ref. You can't mutable ref a mutable ref. Okay. Do my tests pass? My tests still pass. That's good news. What if my pointer points to one valid byte and I write 4? Exactly. That's kind of what I said, right? You have a car pointer and you assign an int to the deref of it, and then it's like, well, what does that mean, right? Yeah, you've just ruined memory. You've ruined Christmas. C really gives you no guardrails to avoid that. Okay, so we've now simplified value writing, and we only write 1 byte for cars. This is good news. This is good news. Let's write a test to assert this, because it does still make me a bit nervous. I'm still not convinced. I guess this is a functions test. And I think the thing we want to test here, it's hard because we really want to test that the size of the locals is correct. So actually in this case, I don't think we want to use the run program like everything else. Let's call this test local size cars. And if we grab our main function, let test equal right, so we grab a main function which has 3. Let's make one of these a car. Let's make 2 of them cars, because ints need to still be 16-bit aligned. They still need to be 2-byte aligned. So if we have 2 cars, we would expect this will only take 4 bytes. Cool. So now we need to compile this, but not run it. We're not actually going to run it in a VM. We're just gonna copy what we're doing from lang common. We're gonna copy how we compile it, right? So run parser compile. Parser st, the program here. We compile the program, and res here is a context. So we should be able to inspect this. We should be able to get functions, and then we get a block, and that block we should be able to say, what is the size of our locals? But here we only have a count. How does get local work? Self.locals. Locals live in a scope. Okay. So this is harder, right? We need to report a total size, I guess. And then we need to reference locals. Oh, we can't just do an index anymore. Okay. So currently, when we have locals, right? They're just done by index. This one lives at offset 0, this one lives at offset 2, the next one would be offset 4, the next one would be offset 6, etc. We do the same thing with args. The first arg would be at offset 0, then 2, then 4, etc. What I'm proposing is a change that would allow us to have local 0 at 0. Local 0 is always at 0. Local 1 would be at, it could be at 10. Local 2 could be at 20. Local 3 could be at 21, only if it's 1 byte in size, and local 4 could be at 22, right? Only if this one's 1 byte in size, and this one's 1 byte in size. There's some constraints here. So to move towards this world, a world that allows parsing structs by value, that would make it a lot better. It really would, wouldn't it? It really would make it just so much better. So much better. I'm gonna start trying to do this, okay? Let me just run our tests again. Okay, so I haven't broken this yet, which is good. I'm gonna just quietly delete this test. Check the other tests work. run a format. Okay. So yeah, use what did we change here? I'm just going to make a commit before I dive into this very large structural change. This commit says what we did was use helper to write write value of misc size. I think that's okay. That's not my best commit message, but that was okay. Because we added a helper. We want to use this helper everywhere. So here's a problem. We have these locals. Now, this usize is in fact not a size, as I thought it was at first glance. This is an index. So we need to replace this with an offset, right? Where once we had an offset, we now have an index, we now have an offset. The type stays the same, and this is good. This is good news. Maybe this is a sign that I actually need to make this its own type. That probably can't help. Pub struct local def. And this is going to have a name, which is a string. It's going to have an offset, which is a usize. And it's going to have a type. It's going to have a var type, which is a type. Cool. So now this is just a vec of local definitions. Do I need to do anything with this? I don't think I do. Now when we define a local, we also need to update it in the parent block. We have a local count. We're also going to have a local offset. And this local offset is going to represent how much space we need for locals. Every time we define a local, next local index. So now what we're going to say instead is, maybe we'll call it, this will be a non-pub function. We'll say local allocate space. And this is also going to take now a type. And it's going to give us back the offset. So out is local offset. I think we can get rid of local count, but we'll keep it just for now, just in case we still need to know how many there are, just in case that's useful. Maybe. Okay. So we'll get the offset. Now the local offset plus equals t.size bytes. And then we return the offset. And also we need to do this thing for cars, right? So if t out equals this, let's say let adjust, right? So this is either going to be adjust is 0, we're going to have this adjustment of 1, which is, or let's actually call this align, right? If the type is a car, hold on, what is this logic? If our type, if this offset is not divisible by 2 and our type isn't a character, we need to add 1 to it. We have to. That's the law. That's the law of alignment. We can't read an int at address 5 because then we would read 5 and 6. We have to read at 4 or 6 or 8. We have to read from an even address. So if this offset has become odd somehow, maybe because we've assigned a character, we're going to have to be clever. We're going to have to do a clever thing. So if out mod 2 equals 0 and matches so if it's not if t isn't a car, if t is not a car, if t is not 1 byte in size, and actually that's a better way to test it, isn't it? So if size is greater than 1 and we have become oddly aligned, then we have to align, otherwise we don't have to align. How's that for a bit of logic? That sounds sound to me. That feels good to me. I feel very good about this. Okay, we move the offset up, but we move it up now by the alignment, and then we also return out plus align. Okay, either 1 or 0, either 1 or 0. We don't have to align if we've just got cars. Cars can be odd aligned. Everything else has to be even aligned to an even address. So now, what was this function called before? Next local index, which is only called internally, which is good. Now we're gonna say offset equals allocate local space. And we need to now give this a type, which is t, which is wonderful. And we need to say local definition, new, I guess. We'll just like use a function just to save a bit of space because these things are actually pretty compact. And again, I don't think this needs to be a pub. I think this is just can be a fun. New, we're gonna take a name slice. We're gonna take an offset, which is a u size, and we're gonna take a vt, which is a type, which we own, and we're gonna give back a self. And maybe this should be a ref. I think this should be a ref. We'll give back a self, name.toOwned, offset, and var type is going to be var type.clone, because again, this definition should own the data inside of it. I think that's good. I think that works. Okay, so local def. Now we don't do this here. And I like this. I like when the function can take care of the ownership stuff for you. You don't have to think about copying. You don't have to think about toOwned, or, you know, like you don't have to care about the fact these are references. You pass them into a function. This function handles the fact that they're refs. It does that good stuff for you. Okay, so we define a local. Now, this iterator isn't what this is anymore. We need to say for every local definition, if def.name, so if this name is equal to the name we're looking for, then we return def.index, def.offset, and def.var type.clone. Beautiful, beautiful. Okay, this is going to yell at me for a lot of reasons. Local definition, singular. Beautiful, lovely, perfection. Local definition, index, not found in the scope. That's because it's called offset. Perfect, perfect. Index, not found in the scope. Offset. Wonderful. Okay, local definition does not satisfy clone. Locals.clone. Okay, so this should be okay to clone, right? Because type implements clone. All the stuff in it implements clone. We can clone it. Okay, so now if I build, this might do some funky stuff. If I run my tests, we might get some funky results. They might all pass. Yeah, so soft multiply blew up. So did brackets. Why would that happen? That would happen because we probably use cars. We probably don't. Well, no, it happens because we're expecting like index 1, 2, 3, and now we're getting 2, 4, 6. So we're doing extra multiplies by 2. So this is good. This is good. This also draws to attention the problem with the way I was referencing them, I think. Define local. Okay, so we're going to now rename this to local offset. Everywhere we see local index, we're going to say local offset. So this doesn't work anymore, but that's okay. Because now, instead of having to do this thing, we just say local offset times 2, right? We just we get the start of the locals and we add the offset. And that's nice. That's really good. Okay, so I need to, everywhere I say define local now needs to change. Except here, this time it's thrown away. Everywhere we use the result of define local, which might only be in these two places, weirdly enough. What about get? What about when we have block variable? Yeah, now all these places, right? This is an offset, not an index. Offset, not an index. But this is good because we have these helpers assigned from stack to local, so we can rewrite this once, hopefully. Hopefully. Assign deref is okay. Assign deref is okay. So everywhere we have block local, block variable, local. Everywhere we use this offset. And again, this is nice because we have helper functions that are doing this. Instruction add. Yeah, so we just get rid of the multiplied by 2, right? It's nice. It's pretty nice. We need to use this type at some point. There's type checking that's not happening here. MadFlash19, stack-based VM. It is a register-based VM, but it has some pretty powerful stack hardware attached to the ISA. So it's a bit of a hybrid. It's a bit of a hybrid. It is certainly mostly register-based. It looks like it's stack-based right now because all of my expressions, all of the values that the language manipulates go through the stack. But at some point I'm going to write like a register allocator, and some of that will get cut down. I only have 4 general purpose registers, but hopefully I can do some clever things and use registers more. Because right now if you return, so when a function returns, regalloc beloved. When a function returns, it returns a value in the A register, right? So what happens right now is you run an expression of some sort, right? Something puts a value, say you return 5, right? So you have to load 5 into a register. It pushes that to the stack, and then it pops that from the stack into the A register, even though it probably could have just put it into the A register, right? I don't have that level of intelligence yet, let alone anything smarter. So it's all a work in progress. It's all a work in progress. Offset doesn't exist because I forgot to rename this thing because I'm very, very silly. Local offset times 2. Expected U8 found. I deleted the cast, not the times 2. That's really silly. Okay, so now if I run the tests, they're still going to fail for the same reason. But, oh god, perhaps even for worse reasons. But now we can just go through. So from stack to arg, that's okay. From stack, load local adder 2. So this is what we need. Local adder 2. Because this isn't an index anymore. This is an offset. Okay, so we get rid of the multiplied by 2. And that should be it. That should be all we have to do. That's nice. From stack to local. And again, this is now an offset. Okay, so offset as U8. I think I forgot to delete a thing. I think I forgot to... Oh, I forgot to rename a thing, yeah. Local adder 2. From stack to local. Bin op convert. Okay, so what if I build now? That works. What if I test now? Still not quite right. Max cycles exceeded. We hit an infinite loop. That's not good. That's definitely not good. Where am I? Compile, load address 2. Target register, page register, address usize. Bin op compare. Assign from stack to local. So this should work, right? Why doesn't this work? Why doesn't this work? Oh, I mean, probably partly because we're not allocating we're not allocating any space on the stack for locals. So there's going to be all kinds of weird corruption going on, which would explain why we're running in an infinite loop, because we're probably corrupting the return address, which makes sense, which makes a lot of sense. So where does that happen? That is local count. Okay, local count sim define, we define it as block.local offset, right? So now it's just the total offset. However many bytes we need for locals, that's how many we're getting. Does this work? Oh, oh, that feels so good. That feels so good. That was a significant refactor. That's amazing. So we're gonna add lang. We're gonna commit this. We're gonna say lang source allocate locals by size. And we're gonna cargo. What changes are there? Just a bit of pretty minimal stuff. I don't know what happened here. There must be some weird white space thing going on. Git add lang. We're gonna commit this thing. Okay, beautiful, beautiful. Now we need to do the same thing with args. So let's quickly try and do that. Args.iter. This is in the block itself. And again, I might actually just make a type called maybe this is actually maybe this is just a variable definition. Maybe there's no such thing as a local definition. Maybe they're all just variables, right? Maybe it's the same data, just defined in a different place. Variable definition. It's kind of funny that these things, they started out a little different, now they've converged. All right, so define arg. We have a string, we have a type. So args.push, except now it's gonna be variable definition new. We take the s, we take the t. Oh wait, does it have an offset? Wait, do args get pushed to the stack? Okay, no, hold on. This doesn't work. This doesn't work. We're gonna undo this. We're gonna okay, we've reloaded. Okay, that doesn't work because args being pushed on the stack. We need to have a smarter way of pushing args. So we're essentially saying that an argument, you cannot pass anything by value that is bigger than 2 bytes on the stack. You can have locals, so you can't pass a struct by value. You also can't return a struct by value. That's okay. We need some checks to make that a reality, though. Right now, there would be nothing to stop me. Well, okay, let's go back to our lang tests for a second. Let's go lang tests. Let's go struct.rs, right? Because it would be good to have a struct test. We're gonna copy and paste because that's my favorite thing to do with these tests. We're gonna come back to that test I started writing a minute ago. We're gonna say struct on in frame, and this is gonna be for putting a struct inside a stack frame. Okay, so let's say, well, let's define a struct first. Type foo equals struct int x, int y, int z, maybe. Just need a semicolon. Now let's say let foo.f return 5. I think this blows up for some reason. It's actually a parser error, which is weird. Kind of looks like my my parser doesn't understand these declarations anymore, which is weird. It seems like it forgot them at some point. I must have not written a good enough test to cover that, which is annoying, because I have a statement declare. I have a statement when there's no value, but they don't appear to be working. So let's see if we can write a test that fails for this and then work from there. That's usually what I try and do with these parser things. Okay, so let's go test. What are we testing? We are testing, this is a quality comment. Thank you, Mad Flash. We are testing that. Wait, do I have a test for this already? Do I have an inadequate test already? Test declare. Let's just add to this one test. Let's add more cases. Let foo.x equal, well, let foo.x. This is literally just what we're trying to pass, and I don't think it has a semicolon when it's just the bare thing. All right, expect EQ, run parser, and the parser is going to be statement variable declare, which is perfect, and that passes. No, it doesn't. That was a build, not a test. Stir equals statement. What have I done wrong here? ToString. I forgot a toString. Okay. Yep, that is expected. That makes sense. Test declare. Okay, test declare does fail. Huh. Expected token with confidence low. So we broke this kind of declaration. Assign declare. Declare some box new expression. That's interesting. It looks like we actually don't have, it looks like we just don't have this anymore. Where did this go? Did we ever have this? Was this ever actually optional? Maybe not. So this is kind of important now, right? Because we don't have value initialization for structs. That would be hard. Declare no value. Let's give it a really shitty name. Expression. So then we just don't do this last expression. We don't do an equals. Beautiful. And then we just give this none. It is a bare declaration. Does this build? Not quite. S2, S3, S3, excellent. And we should just be able to add this to our statements. Now, we have to try this one last. We have to try this one after we've tried the other declare, because otherwise we'll just see this and we'll finish. Actually, we won't because of the semicolon, but that maybe is why it didn't exist before. Okay, so declare. This is now a declare. Wait, this one's the declare no value. Okay. What's going on here? Context, none, tag, none, kind, expected token, confidence, medium. Because I forgot to put a semicolon. And that's good, right? Because we could see it was more confident. The confidence was, in fact, medium. Okay, now we're back here. Now we're back here. So I'm going to try this one more time, right? But I'm going to try this with just a statement. See if I can just parse a bare statement. Let foo.x. I'm just going to try and grab one whole statement. And that seems to pass. So why does this not work in context? This is always the hard thing. It's like it works. Why doesn't it work in context? Statement. This is it. This is the only statement. So test struct let foo f. Have I done something wrong? Like it seems to understand where this is kind of occurring. Equals. Ah, wait, no. That was silly. It's just that I'm missing my walrus equals. Okay, so now it fails for a different reason. Struct value unsupported. Yes, this is okay. This is okay. So code gen 159. This might actually just be supported now. Declare. So if the declared type is a struct, well, we support that now. We support that now. Nice, and it passes. in theory, we have now created a situation where we could say foo.x equals 5, foo.y equals 99, and f.z equals 128, maybe. Something like this. Maybe we should do values that are over 1 byte, right? Maybe we should do values. Can we? Okay, no, look, let's, and we can do like hex 1ff. We could do hex 2e6, and we could do hex, because we have 12 bits here, right? So we could do 3, 4, C. Okay, so we've got these 3 different values. And again, when we test, it's not that interesting, right? So we're adding a test for, well, add missing bear declare. Cool. So we now have this declare. Now the other thing we're missing from structs, right? We've got, no, I don't even know what's going on this page anymore. We've got the left-hand side, right? We've got, let me try. Let me just try and carve out a little corner here. We have foo.x equals 5. What we don't have is let y equal foo.x, which is a subtly different thing if you think about it. On this end, we need to work out the address of the thing of this x, right? And then assign 5 to that place in memory. In this case, we need to find the address of the thing, dereference it, so that we can assign the value to this thing. So in one case, this is kind of like getting an address, and this is kind of like getting a value. This is kind of like putting a star here, in a sense, if you think about the fact that it's all just pointers at the end of the day. Londmo, assignment versus access, exactly. Makes me appreciate the whole L value versus R value thing in C++ a bit more. I'm like, oh, they didn't just invent those words to make my life hard. They're actually concepts that mean something. So I'm going to try and do this real quick. We're going to need a new expression type. We're going to have to go into AST. We're going to have to go into expression struct. Enum. I always do this. Expression, and it's going to be a field deref expression, I guess. Now, we're going to have a left-hand side of the dot and a right-hand side of the dot, and I think the left-hand side of the dot might be allowed to be an expression, because I would like this to be... No, that doesn't work, does it? Oh, again, because if you chain these together, right? If you have foo dot x dot y dot z, here you're treating this as an address. So this is an address. This is an offset to this address. Well, assuming these are a struct. So this is an offset to this address, which is then itself an address. So you do deref. No, okay, we can do this. We could say expression. Yeah, you could func.x. Yeah, I'm going to allow this. I don't think C allows this. I don't think C lets you say, like, I don't think if foo returns a struct, I don't think you can say foo.x in C. But in my language, why not allow it, right? Why would I not allow that to happen? So you'll have an expression on the left-hand side, and then you'll have a string, which is an identifier, sorry. Why do we use identifier sometimes and string other times? Don't ask. It's better to not ask. So we're going to have a whole expression, then an identifier. And the cool thing about this is this thing could be another field deref. So we can have a recursive structure here, which will hopefully make my life easier, because that's what I'm desperately hoping for. So we're going to add a new type of thing. It's going to be a field deref. We're going to have an expression. We're going to have a field, and it's going to be e.field. Explain why in one sentence. Explain why what? Oh, explain why func.x could be an expression? Or explain why C made decisions, because the string verse identifier. Oh, yeah, yeah. I wish I knew. I wish I understood my brain. You can do foo.x in C. That's really interesting. I didn't know this. So that means that it is treating it like an expression on the left-hand side of the dot, which is the logical way to do it. That makes a lot of sense. I like that. That makes me happy. Okay, there's going to be a few places this isn't covered. In CodeGen, this isn't going to be covered, right? And it's not going to be covered because, well, we haven't implemented it, but we're going to have to think about what this looks like. So we're going to have to find a nice place in this freaking ridiculous, gosh, golly gee. Okay, so we're going to say AST expression, what did I call this? Field deref. We have a left-hand side and we have a field. I mean, there's a lot of stuff that has to happen here. But also not loads. Do I have a step where I undo syntactic sugar? No, but I could. I could add an AST manipulation step. I guess you can split it out into lots of lines, right? That's the other way you could think about doing this. But the recursive expression way works as well. Like foo.x.y.z, you could split it out into you know, t0 equals foo.x, t1 equals t0.y ... That would work. That would work too. That's valid. That's a good point. I don't have the machinery for doing that kind of AST transformation, but that would be interesting to do. Okay, so we dereference the field. The first thing we need to do is evaluate what this left-hand side is, right? This left-hand side is well, first off, this left-hand side has to be a struct. So let ty equals type of, we give it a context, we give it the scope, and we give it a ref to the left-hand side. And if not ty.is struct, oops, accidentally quit Vim. I thought that was supposed to be impossible. No, wait, what is it? And this is this awkward thing again where we're going to end up in this situation of was I the streamer with the parser combinator confidence error? Yeah, that's me. It worked. I did it. I think my brain is getting too fried to do this. It's been 2 hours, so I think I'm going to have to leave this in this weird half-started state. It's like it's after midnight, and it is too late to be thinking about the difference between a pointer to a struct and just a struct in this context. Even though realistically for my code, there actually isn't much of a difference. Oh my gosh. Oh my gosh. What does it mean? Okay, I gotta stop. My brain is gonna spiral on this. I'm not gonna sleep. But that was a lot of fun. But yeah, my parser combinator confidence error, it worked. I did it. It serves me well. Let's find someone fun to raid. Let's throw our viewers on. Let's share the love around. If anyone has a cool raid suggestion, I'm always up for it. Always up for it. Loading, coding, more 3D. That looks kind of cool. That looks like someone's doing some real old school stuff. S Crandall. I'll have a look. If they have too many views, I won't raid them. They do not have too many views. Indie game development in Rust sounds awesome. Let's do it. Let's throw them over there. Unable to raid at this time. Interesting. Let's try that again. They might have raids turned off. Some people do that. Okay, I can't raid them, unfortunately, which is a bit sad. They seem like they're doing cool stuff. Yeah. Cozy game dev, that sounds like it could be fun. RPG plus base builder, that sounds fun. Roguelike, it looks like this person is playing chess. Node graph runner and context. That sounds interesting. Let's try this. Some Vulkan stuff. Node graph I love a node and I love a graph. I like when these things combine. Let's go over and show them some love. Thank you everyone who has been tuning in. We are making progress, okay? Stuff is happening. It's good. We're going to have a real programming language soon with real Struct. So thank you everyone for tuning in. It has been wonderful as always. Thank you to everyone watching on YouTube, especially the people I can see that are really bumping my average view time up. You've been great. I'm Tom, and I will catch you next time.